Back in 2016, the American startup Boston Dynamics wowed the world with the first commercially available robot dog, Spot. Since then, the potential applications and commercial interest for such quadrupeds have only expanded. The key benefit of walking robots is that they can be directly incorporated into environments designed for humans or natural terrain, and can thus assist in tasks directly. In researching this area, we found that current high-quality robot quadrupeds that are expandable and robust for research use are very expensive. Budget models, on the other hand, sacrifice either form or function to meet budget requirements. Currently, if student researchers at Monash Robotics decide to work with a robot quadruped, they have few options. Purchasing a suitable robot would either cost a few $1,000s, making it prohibitively expensive for student projects, or the robot will be too small for use or lacking an aesthetic form. It would also make repair costs far too high to be practical, as shipping parts back to a supplier every time you snap a leg off is just not feasible.
Our project, the design and construction of a low-cost robot quadruped, is a response to this. Nathan and I set out to create a quadruped that was affordable, robust, capable of being expanded or modified for conducting a variety of research, and aesthetically pleasing. Our aim was to design and build an elegant robot solution that could perform fluid motion, all for the cost of only $1,500. After months of design, prototyping, testing and building, we are pleased today to be able to introduce our robot, the Dingo. The Dingo weighs in at just over 3 kilograms, making it easy to transport and move around. It has a length and width of 38 by 25 centimeters and stands 25 centimeters tall in its resting position. It is controlled by a PlayStation controller or via the keyboard of a computer which is connected remotely. The user is able to have direct control over the pitch, roll and yaw of the robot. It can also change its height either at a standstill or while moving, and can walk in any direction. With a top speed of 30 centimeters per second, the Dingo can easily walk through a room or area, allowing for efficient research and data collection. It has a payload capacity of up to 500 grams, making it suitable for carrying additional sensors and actuators for research purposes. It also provides full state feedback in both the joint and task space, aiding the user in the development of advanced control and decision-making algorithms.
The key size and weight constraints of the Dingo were primarily dictated by the motors used, which, as the most expensive part of the robot, were limited by the available budget. Each leg of the Dingo relies on 3 servo motors, each rated to 35 kg/cm of torque for a total of 12 motors. One of the benefits of our design over some others is the unique placement of the leg motors. We have designed our own mechanical linkage that allows 2 motors to be placed on top of one another in a hub, keeping the heavy motors tucked in and reducing the inertia of the leg to aid in smooth movement. While one motor drives the upper leg directly, the other motor operates the lower leg via a linkage, and both motors share the same functional axis of rotation, greatly simplifying the kinematics and reducing the chance of limb collision. The central computer of the robot is a Raspberry Pi running Ubuntu, as well as an Arduino Nano that can be used for extra peripherals and control of analog sensors. The Dingo can be powered using lithium polymer batteries that can be placed under the body of the robot. Using a standard 4.0 LiPo, such as this one, the Dingo may be continuously operated for at least 25 minutes. Power is delivered to parts of the robot via a custom PCB. On top of distributing power to existing components and measuring the voltage of the attached battery, the board has many ports for powering additional 5-volt devices that the user may want to add. And we even have spots to add a 12-volt buck converter for 12-volt power if desired. As you can tell, modularity and expandability have been key points of our design throughout this process. The torso of the robot has a removable front and top plate, as well as 10 spare mounting holes placed on the top. One of our favourite uses for these holes is mounting a carry handle, which can be used with or without the top plate. In future, this could be used for a LiDAR or other laser scanner module for area mapping. To maximise the longevity and performance of our motors, the Dingo features 2 large fans on either end. Under use, these fans reduce the average temperature of the motors by 20 degrees Celsius, bringing the average temperature from 59 degrees down to just 39. When working on the robot, these fans can be flipped up at either end, and when down, they are each held firmly in place by pairs of neodymium magnets. The back of the Dingo is designed to be maximally useful for the operator. Access to USB and Ethernet ports of the Raspberry Pi is easy, and there's also an LCD screen that can be programmed to show useful information, such as remaining battery life or IP address connection details. Finally, the top of the robot features an Australian-approved e-stop. Pressing this cuts all powers to the motors while keeping power to the CPU, ensuring that a user is safe from finger jams or is able to stop the robot if anything goes wrong.
In addition to the physical robot, we have also built a parallel simulation using the software Gazebo. This simulation contains an exact model of the Dingo and can be used to test various patterns of walking, as well as control algorithm changes. Importantly, it could also provide a testing ground for reinforcement learning to teach the robot to remain stable over rough terrain, while allowing direct transfer to the real platform. The simulation has had some slight simplifications made, such as removing the complex leg linkage. However, all of the functions are the same. The simulation can be run at the same time as the physical robot, as the joint angles are published via a ROS topic, which brings us to our next point. The Dingo has been built within the framework of ROS Noetic, a version of the open source robotic operating system. ROS is standard within the research and open source robotics community, and it was essential for all stakeholders that the robot we designed be built using this system to ensure ease of use, expandability, and incorporation into existing systems. By integrating our robot into ROS, researchers in the robotics laboratory will be able to easily deploy and integrate their code and existing packages with the Dingo.
We are proud to say that we have created a robot that can serve as a reliable and adaptable platform for future students and researchers. From start to finish, every decision was made with the intention of facilitating our next users. Our screwless battery access flap, removable foot pads, and our utilisation of brass-threaded inserts in over 80 places to add longevity are prime examples of this.
While we have many suggestions for future work, we believe we have accomplished something significant. By making the robot available through the release of code and our CAD model, we hope to make a valuable contribution to the open source robotics community. We would like to extend our gratitude to our supervisor, Michael Burke, Monash University, and everyone else who has supported us throughout this journey.